Okay, so what we want to do here is we want to talk about what we're trying to estimate, because it's not as easy as it might seem. And even though it's a randomized experiment, we have to figure out how we're going to identify the parameters. Who knows what it means to identify a parameter? Anybody have an idea? Identify. What is that all about? Ever heard that term, identify? People say this. What does it mean? Suppose I have a model and it has a mean. What does it mean to identify the mean? How about estimate from data? Like, what's a good estimate of the mean of a population if I take a random sample of cases? Who can help me?
Actually, from the sample that you use as an estimate for the student population.
Right, exactly. So that's a nice definition of an estimator, right? It's a rule. So we collect some data, we calculate some numbers, and an estimator is a rule for combining the data from that sample in order to estimate some unknown parameter, right? And so, okay, so that's estimation. And identification has something to do with whether the estimator is any good. Any ideas? No? You guys, aren't you taking econ courses? Don't they use that word all the time? I don't know. I hear it all the time. Anyway, so Josh, you know, identify. Josh, he used to hang around with economists at Chicago. I know him, so I'm asking him.
No, it's really something that I
Okay.
have a sense of, but
Yeah.
can't think of how to put in the right thing.
So, okay. So the idea is, basically, it's kind of. Did you have a thought? No. So the basic idea is, if I had an infinite sample size, would that thing I just calculated be what I'm trying to learn about? Okay. So sort of, you know, I guess a statistician would say, is the estimate consistent? Does it converge to the unknown parameter? So here's the way I think about all quantitative research now. I've gotten really moved by this idea of identification. You've got a theoretical model, and in that model are parameters that, in our cases, are something like a causal effect or something you really want to learn about. It's your research question. That parameter is your research question. And your literature review has one and only one purpose, and that is to tell people why knowing that parameter would be just the best thing since sliced bread, right? Knowing the value of that parameter. So you have this theoretical model, and then you're going to analyze the data from a model. You're actually going to go to a software package or something, and you're going to apply some rules and estimate that thing. Under what conditions is the thing that you're actually trying to estimate the thing that's in your theoretical model? If it's the same thing, that's called identified, right? So we might say that if I randomly assign half of you to receive one treatment and half another, and I compute, and so half of you go off and do whatever you're supposed to do, and the other half do, and I want to identify the causal effect of the treatment. We need an assumption under which the mean difference I'm calculating is equal to, or identifies the mean difference I care about. And that's called an identification assumption. So the biggest identification assumption might be, the best would be, I randomly assigned you. If I randomly assigned you, then we know that your potential outcomes were unrelated to random assignment. Therefore, the sample mean difference between your outcomes is an unbiased estimator of the population mean difference, right? Okay, all right. So I'm going to use those ideas, and we're going to try to figure out, yeah. Mike? No, it doesn't, because two things have to happen. Let me ask these guys. So if I have so let's say I want to estimate mu1 minus mu0, and I have an estimator which is unbiased. Does that mean that my estimator identifies mu1 minus mu0? It doesn't actually. On average, over many samples, right? I will get the right answer. But what has to also be true? Consistent. Say more.
In an infinite sample, it has to get the exactly the right answer.
The sampling variance has to diminish essentially to zero as you get more and more data. Otherwise, I have this unbiased estimator, but it's always uncertain, no matter how big my sample size is. That seems kind of hard to, it's hard to kind of imagine how stupid an estimator would have to be for that to be true, but it could happen. All right, so we've already talked about a multi-site randomized trial as being a fleet of randomized experiments. It's like a meta-analysis, right? I've got a whole bunch of sites. In every single site, we've replicated the experiment. But it's better than a meta-analysis because in each site, I have the same outcome variables. It's a planned meta-analysis. And I want to learn from this whole fleet of experiments. That's what we've been talking about. And so I want to learn some things from them. And so I think I might have mentioned, or somebody mentioned, that since 2002, IES has funded something like 175 randomized trials, and most of them are multi-site trials, so most of them are these fleets of experiments. So the purpose of this particular project is to figure out how to learn more from these. And this is pretty much review. Mike made these points that. So what do we want to know when we see when we have a bunch of studies? You're writing a lit review. What do you want to know? You want to know, first of all, probably you want to know whether the outcomes are consistent. Because if they're consistent, then I can say, here's the outcome of this fleet of study, this whole bunch of studies I'm reviewing, and here's what we know. And usually people say, after a long lit review, the outcomes are inconsistent. And you sort of wonder, oh my God, what did I just read that for? But the outcomes might be inconsistent because just of sampling differences. You know, they might have different estimates, but the underlying effect size could be the same, or they might have true heterogeneity, right? So if they have true heterogeneity, we want to know how big the variability is, and we'd like to know why it occurs. Okay, so that's all a review of what we've been talking about. I've got a bunch of recent ones. I'm going to skip over this part. So now I'm going to put out a theoretical model. So here's a theoretical model. We can derive this model just from the fact that each person in a site has two potential outcomes. We can easily derive this model. I'm not going to drag you through it. The model it'll show us exactly what's going to be in these random terms. But what it basically says is that the outcome y for person I in site J is equal to slightly different notation, sorry about it, U0J, which is going to be the control group mean in site J, plus B sub J times Tij. Now Tij is a 1 if you're assigned to the experimental group and a 0 if not. So B sub J is the causal effect on average of T on Y for persons in site J, and Rij is some error of prediction that has some variance, and we'll call it sigma squared T because we're going to allow the variance to be different for the treatment and control group. Okay, clear? And now what we're going to say is that looking across sites, the control group means U0J vary randomly around an overall control group mean plus a random effect associated with each site. Small u sub 0J. The site-specific treatment effects are going to randomly vary around a grand mean plus some site-specific random effect. And we're going to have three covariance terms. We're going to have the variance of the control group means, the variance of the treatment effects, and the covariance between the control group means and the treatment effects. Howard asked you this morning, it's kind of a replay of what he said, slightly different notation, sorry about that. If tau 0b is a positive number, okay, you guys, now I know you know the answer, so you tell me, just to make sure. If this covariance tau 0b is positive, what does it mean? Who can help me? Yes. You can help me?
Oh,
Sure, why not?
If it's positive, that means that the treatment effect
It's very close. What you're saying is almost right, but it's almost exactly right. But you could be a little more precise, a little bit more surprise. So the treatment effect is bigger. Where? Well, it's not just for people. It's in sites.
Oh, okay.
So now finish the sentence.
So in sites that have a higher control group.
Exactly. So it's not really individual. The same thing happens at the individual level, but now we're talking about sites. So if in sites that have, where people would already have done well without the treatment, there's a big treatment effect, positive number, versus, the other thing, and this is something that Howard showed us that we have in the Head Start study, which is that in sites where the kids would have done not very well at all, those were the sites where the Head Start had the biggest effect. So that's a substantively important question, right? I guess it's pretty obvious that the beta is something that we almost always focus on, which is the average treatment effect across the whole population. And we've been talking a lot about the heterogeneity, tau squared sub b, which is how heterogeneous is the treatment effect. But we're also introducing this third parameter which we're resurrecting it from Howard's talk, that this one could also be of interest. And so what I like about this model, it's very simple, but it has three parameters that are causal, right? It's it has three parameters that are causal, meaning, population parameters, the average treatment effect, the variance of the treatment effects, tau squared b, and the covariance treatment effect between the control group mean and the treatment effect. In principle, we ought to be able to squeeze answers out just using randomization. We don't need to bring any covariance in. I don't need to bring, we like theory, but we'd like to do as much as we can with this expensive randomization thing that we just did. Now let me say something about this model. I haven't made any assumptions about anything yet, really. I haven't assumed that that we have normal distribution of anything. I haven't assumed that there are no confounding variables, right? This is just a theoretical model. And that's so when I say a theoretical model, I'm not saying that I'm not even saying you would ever use this to estimate anything from any data. This is just, it just defines the parameters that we care about. This is the lit review leads up to this. Okay, we haven't done any study, we don't have any data, we haven't designed anything. This is just a model of theory. Now we're going to try to figure out, we're going to design a study, and we're going to try to estimate these parameters, and we're going to try to figure out under what assumptions do the parameters that we're estimating from the data that we actually collect identify those three causal parameters. Okay, that's what we want to do. I thought it would be so easy to do this because I've been estimating these models since I did this in my dissertation, 1983. But then I found out it isn't that easy. And even when the TIJs are randomly assigned, see, would you all agree that if we randomly assign the TIJs, with full compliance, just perfectly randomized study, we can identify B sub j in every site. Does everybody see that? We can because all we have to do is take the sample mean difference between the experimental group and the control group as an estimate of B. And if we had enough data, that sample mean difference would be the B. And in finite samples, it's an unbiased estimate with a variance that we can also estimate. We could compute a nice standard error for it. So under randomization, we can easily identify this. And yet what I'm trying to say is identifying this beta, this variance, and this covariance might not be so easy. That's what stunned me when I started really getting into it and thinking about it, that it wasn't as easy as I thought it was going to be. Why not? Well, because of two kinds of imbalance that come about in a randomized experiment. One is we might have equal numbers of people. Different sites have different sample sizes. And the other one is that in the different sites, there might be an unequal, let's call it the propensity score. Okay, let's use that. How many people have heard the term propensity score? Okay, the propensity score is the probability of treatment assignment. T bar J, which is the fraction of people assigned to treatment in site J, is a sample propensity score, i.e., it's the sample fraction of people. It's not the true probability. There's an unknown probability, but let's call it PJ or something. But there's a T bar J is the sample propensity score. So an experiment. So I want to just say one thing. An experiment is unique in that the propensity score is known. And what makes an experiment different from a quasi-experiment is that in a quasi-experiment, the propensity score is not known. If we knew the propensity score, it wouldn't be a quasi-experiment. That's the difference between a quasi-experiment or a non-experimental study that's trying to do causal inference and an experimental study, is whether or not you know the propensity score. Okay? But even though we know it, what we do with it turns out to make a difference. So let's see if I can get you to think about this. Suppose that we have a charter school lottery study, and suppose that we find, so there's a whole bunch of charter schools, and the way they all work is they put out an advertisement in each site, and N sub j people respond to the advertisement. And let's just say, for the sake of argument, to make it simple, that each charter school has some fixed number of places available. And so people are going to apply, and then there's going to be a lottery. And so let's say 20 people are going to be admitted to each charter school. But the number of people applying varies. Okay, so what might you think about the sample size in a site? Is it something that might be, usually we think of a sample size as being fixed by design. Is there any way that that sample size could be correlated with go back to our theoretical model. Is there any way that that sample size could be correlated with this BJ? This is the true effect. This is the true effect on site J. Either that sample size or that propensity score. Any ideas? Because you guys are kind of studying economics, so what might happen? Or, psychology. Or yes?
Since students are applying to these schools, more students may apply to programs that are more successful, so we may expect to have a higher sample size and a lower propensity scores for programs with bigger effects.
Okay, great. So the sample size in a site could be actually a measure of how popular the charter school is. And if people know anything about what a good school is, which is a very open question, it could be kind of a measure of how of BJ. I mean, it could be sort of correlated in some way with BJ. And then the probability of getting in is going to be harder in the more popular schools, right? Okay, so that would mean that the sample size and the propensity score might be correlated with BJ. That's what we just said, right? So that's going to be the thing that's going to worry us a little bit in a multi-site trial. The unequal n per site and the unequal propensity score. So that means that if you have different numbers of people in a site, different propensity scores, you might get different results. But let's keep that on the back burner for a minute. If I want to introduce this other idea, because we still haven't really, so we're worrying about confounding. We still really haven't defined what we're trying to estimate yet, our targets of inference. And I don't know if anybody, I haven't seen anybody talk much about this. I guess some people have. Maybe Peter Chauchet wrote a paper about this. I think maybe Estimands and Estimators, a few people have written about this. If we're trying to generalize to a population of sites, we should probably think about the beta, the overall average treatment effect, differently than if we're trying to generalize to a population of people. Okay? So let's imagine, so right now what I want to back up a minute and talk about, well, what are we shooting for? What's our target? What's the goal of this study? Well, we have our theoretical model, we have our beta, but what is beta? Okay? And then we're going to evaluate different estimators, and we're going to evaluate them when we worry about the possible correlation between the sample size or the propensity score and the mean of the site mean treatment effect. So right now we're backing up, trying to figure out our target of inference. And so if I wanted to generalize to a population of sites, I might just take, if I knew each B sub j, so I know the true effect in each site j, and I have a population of size j star, some huge number, like in the Head Start study it would be what, 35,000 or 40,000 sites across, something like that, some huge number of sites. We do the Head Start study where actually there's a list of all the Head Start centers in the US, and it's some giant number. What is it? How much? 18,000. So in Head Start, J star is 18,000. And if I knew the BJ, that is the effect of being assigned at random to Head Start in every site J, I would add up from J equals 1 up to 18,000, all of the BJs, and divide by 18,000, and I'd have the mean of the site means. Okay? That would be an S. So I'm going to call that beta sub sites. That's different from maybe beta sub persons. Because maybe what I really want to know is, what's the average effect of Head Start in the population? Now we've got to be a little careful. What would it be? The population of all eligible children? Every child in the United States who's eligible for Head Start. And I don't know, somebody probably knows how big that, I'm not sure we know that on every site, do we? See, they didn't, when they took their list of all the Head Start centers and then they took a probability sample, I don't think anybody ever said, well, let's get a list of all the age-eligible children. Let's take a probability sample of them. They never did that. What was it, Howard? It was just it was people who applied, right? Who oversubscribed. Oversubscribed. So it's like the lottery thing. It's a little bit like the lottery thing that I was saying. So oversubscribed. They put out an advertisement. People who were and people applied, and then they were randomly assigned. But so that this second generalization would be very difficult in Head Start because capital N sub j would be the site of the number of kids who were eligible for Head Start in site j, and the overall population average. We would take the subpopulation size N sub j, multiply it by the site-specific average causal effect B sub j, add those up and divide by the total number of eligible children in the entire United States, and we would get beta sub persons. Okay? Yeah, Josh.
So I'm trying to think of, like, so we do this a lot where we try to estimate the population, like generalize the population of persons, but in a multi-site context, I'm trying to think of like a situation where we'd ever have like we don't, people usually like ever do what you just described as far as grabbing a population that's representative of something.
It's done in surveys, but I don't know if it's done in experiments. So, for example, high school and beyond, they had 35,000 high schools in the United States. They drew a probability sample. Then they went inside each school. They got a roster of all the children in the school, and they randomly selected sophomores and seniors with a certain algorithm for that. So this is in NELS, National Educational Longitudinal, Early Childhood Longitudinal Study. They all do that. But it is very rare. It's even, well, I mean, as Howard said, it's extremely rare to even have random selection at the first stage from the site population. But but we got to think about this because we still have to think about who we're trying to generalize to, even if we don't have a formal random sample in each site from a well-defined frame of people in each site. We still have to ask, who do the kids in this site represent? And particularly if we're interested in targeting a population of kids, we have to think about that. Now, what a lot of people would do is say that, well, the kids who showed up we don't really understand we don't understand the population. We don't know the population. We can't say what the list of all the elements of that population is. But what we can say is we think these kids are representative of a broader universe of kids who might have experienced this study in that site. And so what they might actually then do would be instead of substituting capital NJ, which is the population size, just put the sample size in each one of these. And say we're just going to weight by the sample size because we want to count each one of our children equally. Okay, that could be a good idea. It could be a bad idea. Yeah, Mike. Yeah.
If you had a study where you had a random sample of sites,
Right.
despite the fact that you didn't literally take a random sample of students, and you use that kind of a lowercase n, then you end up with at least you could get a good estimate of the total number of people in the population. Like if you knew the number of people at your 100 sites in your study and you randomly sample them,
I mean your sample NJ.
you could actually get a good estimate of the top. If you knew capital J, you also have a good estimate of capital.
Yeah, it really depends about how you did the sampling. I mean, I think in some of these school studies, I think there are cases where it's pretty unbiased, but in cases where where you're putting out an ad and you're waiting to see who gets excited and who signs up, that might be, maybe it's a little bit more difficult.
But wouldn't that be true at the student and the site level? Like you don't really know who your sites are.
Yes. No, I mean, this is right. This is right. It's good to think about this stuff. So let's just focusing on the mean. Maybe somebody could help me. Under what conditions would beta sites be identical to beta persons? Because basically through the first century of quantitative social science, people assumed that those would be equal. They didn't say that, but when you saw their models said that. Okay, if the NJ is uncorrelated with the BJs, that's a great point. That's condition number one. There's no relationship between the NJs and the B. In other words, big sites, small sites, it has nothing to do with the size of the effect. That's a great point. That's one condition under when they would be equal. And there's a special version of that condition when two things aren't correlated, right? What else might be true? What have people been assuming from like the dawn of quantitative social science until a few years ago? When you write down the models, most people, not everybody, that would make these equal. Hint: remove the J subscript from the B. Their sites okay. Yes, that's the second thing. If every site had the same NJ, then they would be equal. And that's probably not going to happen very often. But the third one is the one that we've been assuming. Is that a total mystery? Yeah. Exactly. The treatment effect is a constant. And that's really what we've been assigned. That's what we, meaning most social scientists, have been assuming for a long time. The treatment effect is a constant. That's why we don't usually talk about this. We just write down these models and we say we're trying to estimate beta, but we don't say what it is, because we're assuming that if you define it either way, it's the same thing. The mean of the site means is the same as the mean of the people. But if the people are heterogeneous, it could be different if the NJs are correlated with the BJs. And if they weren't, then it still wouldn't be a problem. Okay, so this is still part about being fussy about our theoretical model. We wrote down a theoretical model, but until now we really didn't know what the betas meant. And then the same thing can be said for the variances. We could say the variance between sites is just the average squared discrepancy between the site causal effect and the average, right? Divide by J star, 18,000 sites. And we could say that our other causal parameter, the covariance, is just an unweighted average of these. Whereas we could say down here, generalizing to a population of persons, we could say tau squared beta persons. Well, what that really is, and Howard and I have a lot of discussion about whether anybody would ever care about that, is if you thought of everybody in the whole population as having a treatment effect, and you thought there's a variability in the whole population of treatment effects of people, this is the part of the variation that lies between sites. It's effectively attributable. It's attributable to the fact that the site that sites have different that there's a discrepancy between the effect in site J and the overall, but it's weighted by how many people there are. Okay, and the same thing for the covariance. All right. Okay, so now what we've done is we've written down a theoretical model, very simple, and we have taken one more step to make sure we know what we're doing. Now, we still don't have any data. We haven't designed a study. We're just trying to figure out what are called parameters, or some people call them estimands, the things you're trying to estimate. And we're going to do one of these. We're going to focus more on this one. Particularly, a lot of the studies that we have in mind, we think this might be a little bit more plausible. But we'll talk tomorrow when I talk about complier average causal effects. We're going to have to talk about this one because we just can't avoid it. So now we get to identification. So identification, which is how do we now write down a model that we can actually estimate from the data, and then and define the assumptions under which that model will identify the parameters of the model that the theoretical model we just spelled out. So one thing you can do is you can just say, well, let's just estimate the model, the theoretical model with, let's just use some kind of algorithm, an HLM or something, to estimate that. So that when you take our theoretical model and you combine them, that's what you get, right? Do you see? I hope you see the connection in the outcome for person I in site J. Mu0 is the grand mean for the control group. Again, beta is the overall average treatment effect. U sub 0j is the random effect associated with site J for the control group. Bj is the random component associated with the treatment, and then there's an error. Just is it real obvious? I don't know. Let me just go back, and it's this model. I kind of like this way of showing what's going on, but if you take the U plus U0j and plug it in up there, and you take the B plus Bj and plug it in there, you get this. You get this. And so what people would say, what statisticians would do is, well, they'd say, well, let's figure out, to identify this, to see if this identifies our theoretical model, and we're going to run a regression of some kind or other. What's the expected value of the outcome conditional on your treatment group assignment T, whatever that be? It could be a 1 or a 0. What is that? And what we find is, well, it's mu0 plus beta times T. Those are the two parameters we want to estimate. And then it's the expected value of these error terms given T. So U sub 0 JT says that this is the expected control group mean given that you were assigned to the, T, whatever it was. Okay? And then we get this one too. What's the expected treatment effect discrepancy in site J, discrepancy for the mean given that you were assigned to T? And normally we would just say, well, those have to be 0. And the reason is your control group mean isn't going to depend on your treatment assignment because you were randomly assigned. So if everybody's assigned with 0.50 probability, okay, then there's no way my control group mean can be related to my probability of treatment assignment because everybody has the same probability of being assigned to the treatment. It has no effect, no relationship with these things, except Tij, which is the 1, 0 you were assigned with, actually is composed, Tij, I should think of Tij as being Tij minus T bar j, that's the within site part, and then T bar j. So part of Tij is the site-specific propensity score. So if the propensity score is associated with the control group mean, or the propensity score is associated with Bj, then you have a problem here. And we just said this could happen, like in a lottery study, we said, maybe in the most popular lotteries, it may be the case that that you have the smallest chance of getting in, and if you get in, you get the biggest possible effect because why? It's a good lottery. It's a good charter school. So all of a sudden we have to make strong assumptions. If we assume these things are 0, if we assume that the control group mean and the treatment effect are completely unrelated to the propensity score, then we can, that's an identifying assumption that means that this model, if we estimate it, will equal, the parameters will equal we're estimating the parameters we want. But that's a big, strong assumption. And that would only work if we were generalizing to a population of persons. If we were generalizing to a population of sites, we'd also have to worry about the relationship between these random effects U0 and U1 and NJ. Are there any questions about that? So what we do, so here's the logic. We write down, yeah, go ahead.
So I'm looking at the expected value U0.
Right, so this one says, yeah, this one says that being in a site, the expected value of how effective your site is in producing a good treatment effect is unrelated to the propensity score. If this is not 0, then we're going to get a bias. Okay. So, and this has been kind of the classic. You've probably seen it maybe in some of your introductory classes in econometrics, that critique of the so-called random effects model. That maybe the random effects of the model are correlated with the predictor variable. And here it's happening even in an experiment, okay? All right. So what are we going to do about it? That's the question. Well, what a lot of economists would say is, we're not going to use a random effects model. We're just going to use a site fixed effects model. How many people have ever heard that argument? Just, how many people? How many people never heard that argument? Never heard. How many are abstaining from this question? It's very well established, going back to Hausmann, 1980, Madala, 1978, Mundlock, those guys, they said that. And the idea of a fixed effects model is that you put in a whole bunch of dummy variables, one for each site, and what that does is it just removes the between site variation, and it removes those random effects. And so those random effects, okay, let's go back a minute, just a second. Let's see what's really happening here. Those random effects, this U0 has everything that we didn't measure that might be related to the control group mean. This BJ has everything that we didn't measure that constitutes, or that is the site-specific effect on the treatment effect. Okay, all that contextual stuff that Mike was just talking about is just sitting right up here. And so let's get rid of this stuff by putting in a dummy for every site, and then we'll get rid of it. And so we're going to talk about that. Then we're going to talk about what Howard presented, which is I didn't label it here as such. I should. Centering the HLM and we can center it on just the right-hand side of the equation or on both, but we'll just do it on both. And that's called the fixed intercept random coefficient model. And then we're going to talk about a couple of other ways of doing this. Okay, the fixed effects model. So the question is going to be, is it the magic elixir that you were taught it was? And the answer is going to be no. And for two reasons. And we'll see what they are. Well, I'll tell you there now. The first reason is it's a model that assumes homogeneity of treatment effect. Okay, wait. This young lady right here, homogeneity of treatment. That's what it assumes. And that assumption is consequential, it turns out. If it's violated, we can have a bias. The fixed effects model can be biased. And that's one problem. And so how do we address that problem? The second thing is that it reduces the number of things that we can study. Now we can only study if there's a big consequence of thinking that the effects are constant, which is that there's no variance and there's no covariance between the control group mean and the treatment effect because everything's a constant. So if you assume that, then you're not going to study those things, right? I mean, if you assume something is null, then you don't study it. So we don't study those things. Those are the two problems that I see. So what is the potential bias if we have heterogeneous effects? Because so we write down to see what's going on. We can kind of see it this way. The expected beta hat is going to be the site-specific estimate of the treatment effect. It's going to be nothing more than the sample mean difference between the experimentals and the controls in site J. That's all it is. The expected value of that, oh no, I'm sorry, that's not right. I'm sorry, that's these things. Okay, the beta hat is the site fixed effects estimate of the overall mean. Conditional on the beta hats, the true B's actually. These are the true effect sizes in each site and the propensity scores. And what the site fixed effects is actually doing, it's actually estimating a weighted average of the site-specific estimates, site-specific effects, BJ. And what it's weighting by is the inverse of the squared standard error that you get out of a t-test. So I don't know if you think of it as an OLS estimator with site fixed effects, but when you actually do the math and you have a binary predictor, it just turns out to be this weighted average. So doing a site fixed effects model, and it makes perfect sense because you're taking the sampling precision from each site and you're weighting the data from each site by its precision. And it just seems like the obvious best thing to do because where you have more data, you have more precision, you have larger N. And where this thing is large, you have more precision, you're giving more weight to those sites that are estimated more precisely. They have less sampling variance. I don't know if this thing, can you recognize this as being the denominator of this, the square root of this is the denominator of the t-test, okay? It showed up in Howard's slides, okay? So that's fine, except, and see, because these are assumed to be constants, and the beta hat isn't, but the things that beta hat estimate are constants, and then of course you're going to get exactly what you want. So that seems to have a lot of, it has perfect logic as long as you have homogeneity of impact, because you've got J unbiased estimators of the same parameter, and you're weighting them by your precisions, and we know that's the best thing to do. But if they're heterogeneous, then that means, now what did you tell me about in this lottery study we just mentioned? There might be a correlation between the true effect in site J and the sample size and the propensity score. So what are we really doing here? If that were true, that the most popular sites are that have the largest impacts, and what is this really doing? What's it telling us? What are we doing then? You're overestimating the true effect size because you're giving the most weight to the most popular ones, and if the most popular ones are actually the best in you. Yeah. The mean of the site means, yes, thank you. Yes, the estimate, yes, and that's a very good point, because if your estimand is the average of all of the people's causal effects in your study, then this might actually be pretty good. Because in particular, if these propensity scores were equal, it would just be weighting by NJ, which is a perfectly reasonable thing to do. So that's a really important point that Howard just made, because how good the estimator is depends on what you're trying to estimate. That's why you have to go through this little exercise at the beginning saying, not only what does the literature say and what is your research question, but what are you targeting? What parameter are you targeting? Because it might make a difference, yeah.
But in that case, we'd want to center on the treatment variable in our fixed effects model, even if that's the case, right? Because if we don't do that, then the standard deviation of the probability of treatment would end up potentially weighting our betas, right?
Say that again? I'm sorry.
So if the propensity score is
Yeah.
is correlated with beta,
Right.
we still have some.
We still have some bias. So even if if our goal was to estimate, now imagine these T bar J's are constant, same propensity, but the NJ's vary. Then what's going to happen is these are going to go outside of the sum. It's just going to be the sum of NJ times BJ over the sum of NJ. That's exactly what we said was the estimand if you want it generalized to a population of people. But if the T bar J's aren't constant and they're correlated, then we can with the BJs, we can still get a bias. Yeah. And so here's going to be just a little tip-off. If we weight the data inversely with IPTW, if we weight the level 1 units inversely proportional to the probability of, to essentially T bar J. Well, if you're in the experimental group, we weight you inversely proportional to the probability of being in the experimental group. In the control group, we weight you inversely proportional to the probability of the control group. Then that alone would make this an unbiased estimator of beta subpersons, but not of beta subsites. So you got, so if you didn't know what you were estimating and you really wanted, you'd be estimating beta subpersons, and you'd be lucky. You'd hit the, but I don't know if that's really what you wanted to estimate. Yeah.
So one thing that struck me.
Yeah.
So T bar times 1 minus T bar, which I was mentioning this one,
Right.
doesn't vary all
Right.
the
Right.
unless T bar
Right.
really varies.
Right.
N could vary
Right.
a great deal.
A great deal.
So it feels like
Right.
your bigger threat
Right.
to the cross-site and T bar, yeah, in theory,
Right.
it's a threat, but it doesn't feel like it's necessarily a material threat.
Right.
Well, I don't know. Like, it's in the charter studies. I've never seen, but you can imagine lotteries that are 90%, that have only a few kids on the waiting list, and some that are.
Yeah, you don't have to imagine that. I just finished a big charter school lottery study. In every grade, in every year, in every school, there's a lottery, and the number of people who are offered a place is equal to the number of seats that become available. And sometimes, you get these things where there's very few seats. Nobody wants to leave. And lots of people want to be there, and you get these really low probabilities. And you have these other lotteries that, in fact, there are these so-called degenerate lotteries. They're not even oversubscribed. Or there's, a probability of 0.99 because there's only, there's 9 seats, and, there's probabilities, there's only just slight oversubscription. So it could happen. It's something to look at in your data. That's one. Where we're going to go with this is we're going to get some tools for looking at any particular. Well, first of all, we want some tools for plan. We want you to be able to know what you're trying to estimate. We want you to be able to design your study in line with what it is you're actually trying to what question you're trying to answer. But if we have data that are sort of sitting there that we want to analyze, we want to have some tools that kind of diagnose the likelihood. Some of these biases may never turn out to be anything. In fact, I've got some examples where this bias, I'm talking about this, I'm sort of dramatizing it because I want you to understand it. But where it's really, we can anticipate just looking at the sample sizes and the propensity scores, and so we can actually tell you how likely it's probably not going to be a very big bias. So, but there are other cases, as Sean points out, where it might. In statistics, what we try to do is we try to develop methods that work generally, not just in one specific case or in 2 specific cases. Okay. So here's another way of writing what Howard called the FIRC, the fixed intercept random coefficient model. I kind of like this because it's kind of a simple way of saying what's going on. What we're really just going to do is we're going to center the left side of the outcome by we're going to deduct the sample mean from everybody's score. And we're going to deduct the sample mean of the treatment from everybody's treatment. And that makes the equation within each school so simple. We're just going to regress these deviations on these deviations. This is basically what happens in fixed effects. If you want to know what goes on deep in the heart of Stata when it does a fixed effects model, this is actually what it does. It does the regression. But we're making a little bit of a difference here. You see, what we're doing is, in fact, okay, we're going to say that the treatment effect on site J is beta plus BJ, and that BJ has a normal distribution with a mean of 0 and a variance tau squared B. If this B is 0, this is going to give us exactly what we get out of the fixed effects model. So one way to think about this is we're taking the fixed effects model and we're just adding a random coefficient. Okay. So I'm gonna tell you that at least for the purpose of estimating the mean of the site means, I like this model better than the fixed effects model. I'm going to show you that in fact, we can prove that the bias will always be less than the fixed effects model. bias. And I like it because it gives us a nice way to estimate tau squared b, the heterogeneity. What I don't like about it is it gives us no way to estimate the correlation between the control group mean and the impact. So we'll never know, we can't estimate from this whether impacts are bigger in sites where kids would otherwise do better or worse. We can't do that here because by centering, we've gotten rid of the control group. We've thrown the control group mean out. So we have this. So what do we really get out of this? We get this equation, which is looks scary, because this says that the variance of our beta hat is the sample mean difference between experimentals and controls no, not that beta hat. I'm sorry, I did it again. Beta, forget what I just said. Beta, this is the variance, this is the variability across sites of the true effects, site-specific effects. This is the sampling variance of the estimate within site J. So the total variance of the site-specific estimate is tau squared b plus this. Okay, now I want you to, this is going to involve a little spatial reasoning and a little algebra here mentally. If you set tau squared b, if you set it to 0, okay, and then you reciprocate, this is going to become the numerator, and this is a constant. So if I set this to 0, I'm going to get the fixed effects estimator. It's going to be exactly the same thing. Okay. But if it's not 0, my weights are going to be less variable. In fact, as tau squared b goes up relative to this piece, the weights are going to move toward 1.0. So what this model is going to do is going to say tau squared b measures heterogeneity. If I knew how heterogeneous the impacts are, I'm going to put less weight on these sampling precisions, because I'm really kind of worried that they might be biasing the results. They might be causing a problem. And in the extreme, I'm actually going to just weight, if tau squared b is big enough, I'm just going to weight these things equally. Okay? And what that does, so as the heterogeneity increases, this tau squared b increases, and the reliance on the fixed effects sampling precision weight diminishes. And for that reason, we can prove that if there's a bias in the fixed effects, we can prove two things. This estimator will have the same bias that has the same direction, but it's going to be smaller. And in many cases, quite a bit smaller. So we kind of like that. Still worried a little bit about bias. But the other thing we can prove is that this, in general, this estimator will have smaller variance, sampling variance. So it's got a smaller bias, it's got a smaller, that means smaller sampling variance. That means it has a smaller mean squared error. I don't know if that term ever. Mean squared error is the square of a bias of an estimator plus its variance. So it's gonna be, on average, more accurate. Doesn't mean it's a great estimator, but it seems like it's better than the fixed effects estimator if the goal is to generalize to a population of sites. And it gives us, out of this, we can get a good estimate of the variance of the treatment effects. And this thing looks horrible, but it's basically the same idea. We weight by the inverse of the squared inverse of the variance. We weight these things. Each beta hat minus each site-specific estimate minus the mean squared. Take off the sampling variance. That means each site is giving us an unbiased estimator of tau squared, and weight them by the square of their inverse of their variance squared, and we get this. And so this kind of has, it's ugly, but it has the same. And this is iterative. The reason you see the m's is because this has to be done over and over again. You have to re-estimate the mean. You have to re-estimate the tau squared, and we get this estimate. And we think these estimates that you get out of this procedure are actually pretty good. I'll just briefly say that the other way in the literature that you can try to remove the bias is by actually just run an HLM model, the same model we had in our theoretical model, but put the T bar J, the propensity score that we were worried about, put it in as a predictor. But of course that'll work if the goal is to generalize to the population of persons. Well, it'll give us a good estimate of the mean, but the problem with this one for me is that I'm not convinced that the estimate we get of the variance of the treatment effects works very well. So I'm not going to say too much more about that. Okay. All right, let me... So these options, so the fixed effects estimator, we can only estimate the mean. We don't estimate the variance or the covariance that we care about. So that's limiting. The estimate of the mean is probably pretty good if we want to generalize to a population of persons, but probably not very good in many cases if we want to generalize to a population of sites. The FIRC is better in that we can estimate the mean and the variance, but it still can be biased, although the bias, when we're generalizing to a population of sites, although the bias is smaller. So it's kind of better for that purpose than the fixed effects estimator, but still doesn't enable us to estimate the covariance between the control group mean and the treatment effect, and still can have a bias. So there's something that we can do actually to identify, that is to consistently estimate, remember our discussion, all three parameters and basically be sure that we're doing that. And there's something we can actually do to do that. So it sounds like magic, but even this has a problem that we'll discuss, maybe. And basically what it is we are going to, in our student level data, we're going to define a weight that if you are in the treatment group, we're going to weigh you inversely proportional to your propensity score. It's called inverse probability of treatment weighting. If you're in the control group, we're going to weight you inverse proportional to the probability of getting the control treatment, which is what you got. And what this weighting is going to do, it's going to simulate a study in which every site has the same propensity score. Okay, it's just in the weighted data. In the weighted data, every site has exactly the same propensity score. Therefore, the propensity score cannot cause a bias. And here's just a way of writing the formula, just a way of saying these two things in one statement. The Wij is Tij. That means the 1 if you're in the experimental group. 1 minus Tij is a 1 if you're in the control group. So that's called an inverse probability of treatment weight. Notice we put the sample-wide average propensity score here, t-bar, and 1 minus t-bar, and that makes these weights they have a mean of 1, and in the experimental group, the mean is going to be t-bar, and in the control group, it's going to be 1 minus t-bar. So that's going to really make everything work just beautifully. So that gets rid of any confounding that we might have with the propensity score. Now we're going to add some design weights to the propensity score weights. If our goal, I'm going to start down here. If our goal is to weight every site equally, in other words, we're interested in the population mean, the mean of all site means, I'm going to take the propensity score and I'm going to multiply it by the average sample size divided by the sample size in your site. And what this is going to do is it's going to, in the weighted data, make you have a design that's totally balanced. The same sample size in every site and the same propensity score in every site. And then we're going to weight the level 1 units equally. If we want to generalize to a population of people, we're going to use the IPTW, the inverse probability of treatment weight, at level 1, meaning at the person level, and at the site level, and that's going to make sure that every site has the same in the weighted data. Every site has the same propensity score. But then we're going to weight the estimates by how many people there are in a site. So we're going to apply these two weights. We're going to estimate. We are then going to estimate our theory, going right back to the very beginning. We are going to estimate our theoretical model. Estimate the entire theoretical model, just with those weights. Because now we have a perfectly balanced design that can't have any of the confounding that we're worried about. And therefore, we're going to get everything out of it we want to get out of it. We're going to get the mean, we're going to get the variance and the covariance, estimated consistently. All of our parameters are identified. Magic. Except, why isn't it magic? Any ideas? What's the possible problem? With this. Like, what might happen if, and I think it was, let's see, the Head Start study had some sites that had, what, 30, 40, 50, 60 people, a few. And they had a whole bunch of sites that had 2 people, 3, 4. I'm now reweighting them so that they all have the same sample size. And I'm going to count them all equally. Can you imagine, anybody got an idea? Imagine a scenario where things would go awry with that. I'm weighting them all equally, even though some of the sites have huge sample sizes, and many sites have very tiny sample sizes, weighting them all equally. What can happen? Josh knows. Anybody else? Well, think about the sampling error. Okay, I've got a site with two kids. The sample mean difference between 2 kids is y1 minus y0. It's the experimental score for that one child who was in the treatment group minus the control score. That one child was in the control score. And I'm going to weight that number, that difference between those 2 numbers, equally to 30 or 40 kids from this other site where the mean is it's a mean taken over lots and lots of kids, and I'm going to weight those equally. You see what might happen? The sampling error of that weighted average could become very big. So this is a beautiful result. If you have a huge enough sample, you should get consistent estimators. But in any finite sample, if the NJs vary a lot, which is when you really want to worry about the bias, or the T-bar J's vary, you might end up with a large standard error. So it could be, it's unbiased. It is unbiased. We can prove very easily that it's unbiased for either one of our estimands, beta sites or beta persons, tau squared sites, tau squared persons, or the covariance sites, either one. But it might become highly imprecise. And so that's a paper that I distributed. It's a rather technical paper. We're working on trying to figure out exactly how big these differences can be. I mean, the problem with the biases I mentioned is they don't go away when you keep adding more and more sites. They just stay there. So they might be small, but they just stay, or they might not be small. The problem with this beautiful weighting scheme is that it gives you a great result on average, but how many dissertations are you going to do? Do you want to be on average right across the thousands of dissertations that you write, or do you want your dissertation to be right? Well, you want to have a sample. You don't want your sampling variance to be too big, because then your dissertation might be over here, even though the thing you're trying to estimate is here. I think we might be done. There's some more details about how you actually do this. If you guys do the quant stuff, you use a weighted log likelihood in a 2-level model. You weight the level 1 and level 2 by their weights. It's kind of beautiful how it works out. It gives you the estimates that the estimators that you hope would be the ones you would get. I won't go over that, but basically I think I've said mostly. One other thing I want to say. Once you have, here's another nice thing about simulating a balanced design. Once you simulate a balanced design, and you're using this normal theory, and people criticize hierarchical models, they're based on normality, maybe the data aren't normal. But once you have a balanced design, the maximum likelihood estimates are simple method of moments estimates that you don't have to make any distributional assumptions. You can use binary outcomes or whatever you want. Any reasonable quantitative outcome can be used, or categorical. Categorical meaning binary. So that's kind of a nice thing too. But as I said, the problem is they may be somewhat imprecise. So we can extend these to other designs. And the other thing I like about this, and where I want to kind of go with this, is we can so once we know how to manage these propensity scores, we can take this to the case where we actually have to estimate the propensity scores, which is the quasi-experimental case. We don't have randomization. So this becomes a paradigm, sort of a template for doing multi-level observational studies where we don't